Recently, the James Webb Space Telescope, JWST, has detected mysterious little red dots from the early universe. One special object, called QS01-Able 2744-QS01, is particularly strange. It hosts a giant black hole, about 50 million times the mass of the Sun, but has almost no surrounding galaxy, only primordial hydrogen and helium gas. This discovery revives the idea that primordial black holes might have existed since the dawn of the universe, or at least that supermassive black hole seeds could have formed directly from collapsing gas. However, this is not yet conclusive. Scientists need more detailed observations, such as spectroscopy, X-rays, or gravitational lensing models, to distinguish primordial black holes from other possible astrophysical explanations. 1. What are primordial black holes? A brief concept and history definition. A primordial black hole, PBH, is a hypothetical type of black hole that formed within the very first seconds or even milliseconds after the Big Bang, not from the collapse of stars. In the extremely hot and dense early universe, large density fluctuations, overdensities, phase transitions, or topological structures, for example, cosmic string loops, could have caused regions of matter to collapse rapidly into black holes. The idea was first proposed in the mid-20th century and has been widely discussed since then. Properties. Unlike stellar black holes, PBHs are not restricted to stellar mass ranges. They could span a very wide range of masses, from very tiny ones, which would evaporate due to Hawking radiation, to millions or even trillions of times the mass of the Sun, if initial conditions allowed. Some theories suggest that PBHs could account for part, or even all, of the dark matter within certain mass ranges, though this is strongly constrained by observations, CMB, microlensing, gravitational waves, etc. 2. Formation mechanisms of primordial black holes. Scientists usually divide the possible ways primordial black holes, PBHs, could form into two major groups. 2.1. From density fluctuations in the very early universe, right after the Big Bang, the universe went through a period called inflation, an extremely rapid expansion. During this phase, some tiny regions developed density fluctuations, where matter was more concentrated than the surroundings. As the universe kept expanding and cooling, these regions re-entered the cosmic horizon during the radiation-dominated era. If the density was high enough, gravity would overcome radiation pressure, and the region would collapse into a black hole. The mass of the PBH depends on the cosmic time when the fluctuation entered the horizon. The earlier it happened, the smaller the PBH. The later it happened, the heavier the PBH could be. 2.2. From other special physical processes in the early universe, besides density fluctuations, several other phenomena could also create PBHs. For example, cosmic phase transitions. Just like water turning from liquid to solid, the early universe also went through phase transitions as its temperature changed. These transitions could produce regions of extremely high density, which then collapsed into black holes. Cosmic defects, strange structures such as cosmic string loops, formed by irregularities in energy fields, could shrink and concentrate matter so strongly that they collapsed into black holes. Direct collapse. In this scenario, huge clouds of gas in the young universe collapsed directly into massive black holes without forming stars first. Although this process happened later, hundreds of millions of years after the Big Bang, and thus is not primordial in the strictest sense, it could still produce very massive black hole seeds, the ancestors of the quasars and supermassive black holes we observe today. In summary, These hypotheses suggest that primordial black holes could have been born in many different ways, from tiny ripples in the early universe, to exotic physical processes, to direct gas collapse. This diversity makes PBHS a fascinating subject, connecting theoretical physics with key questions about the origin of dark matter and the formation of supermassive black holes. 3. What signs suggest that an object might be a primordial black hole, PBH? Primordial black holes, PBHS, are very difficult to identify, since they do not emit light and have no label to distinguish them from ordinary black holes. Therefore, astronomers can only infer their existence through indirect clues, by observing their surrounding environment or the gravitational effects they produce. Some important hints include 3.1. Star-poor environments with strong energy sources, normally, supermassive black holes at the centers of galaxies, like quasars, are accompanied by generations of stars that nourish them. However, if astronomers discover a quasar-like light source whose radiation comes only from primordial gas, hydrogen and helium, without heavy elements, it indicates that the region has never formed many stars. If a massive black hole is found there, it could be a PBH candidate or at least an unusually early black hole seed. This is exactly the remarkable property observed in QS01 with the James Webb Space Telescope. 3.2. Mass far too large compared to surrounding stars. When observing a galaxy or cluster, scientists can estimate the central mass concentration by measuring rotation curves, stellar orbits, or gravitational lensing. If the central mass is far larger than the number and mass of visible stars can account for, it cannot be explained by normal galaxy evolution. In such cases, a PBH becomes a plausible hypothesis. Thanks to JWST and gravitational lensing experiments, several such candidates are now emerging. 3.3. Lack of heavy elements and extreme youth. Stars create heavy elements, called metals in astronomy, through nuclear fusion. If spectroscopy of a light source shows only hydrogen and helium, with no trace of heavier elements, it means the region existed before multiple generations of stars had enriched the environment. A giant black hole found in such a metal-poor environment is a strong candidate for primordial origin. 3.4. Gravitational waves from mergers. If PBHS exist in binary pairs, they can orbit each other and eventually merge. This process releases enormous energy in the form of gravitational waves. Observatories such as LIGO, Virgo, and in the future LISA or the Einstein telescope, may be able to hear these unique signals. By analyzing the frequencies and patterns of these waves, scientists could uncover evidence for a whole population of PBHS in the universe. In summary, scientists still have no way to directly observe PBHS, but they do have many indirect clues. Whenever a black hole is found in an unusual environment, too few stars, lacking metals, disproportionately massive, or producing strange gravitational wave signals, it may open the door to the mystery of primordial black holes. 4. New evidence. QS01-Able 2744-QS01- as seen by JWST. This week's most exciting discovery comes from the James Webb Space Telescope, JWST. Astronomers detected a tiny red dot, named QS01, located behind the galaxy cluster Able 2744. Thanks to gravitational lensing, QS01 appears as three separate images. Remarkably, it dates back to the reionization era, less than 1 billion years after the Big Bang. A huge mass analysis shows that the center of QS01 weighs about 50 million times the mass of the Sun, far larger than the few stars around it. A pristine environment, The light spectrum reveals almost only hydrogen and helium, with no signs of heavier elements usually produced by stars. This means the region has seen little to no star formation before. Implications: the unusual combination of a supermassive black hole without a developed galaxy makes QS01 a strong candidate for being a primordial black hole, PBH, or a very early direct collapse black hole. This challenges standard theories of how supermassive black holes form. Still, researchers remain cautious and avoid drawing final conclusions for now. The discovery of QS01 suggests that in the early universe, giant black holes may have formed in unusual ways. Although we cannot yet confirm that it is truly a primordial black hole, this evidence opens a new direction for studying the origin of supermassive black holes and the evolution of the cosmos. In the future, deeper observations with JWST, Euclid, and LISA will help humanity answer a crucial question: do primordial black holes really exist? Thank you for watching. If you found this content interesting, don't forget to like, share, and subscribe to the channel so we can keep exploring the mysteries of space and the universe together. See you in the next video.